Good evening, everyone. Welcome to the tutorial session for the course Classics in Total Synthesis. I am Sri Lakshmi S, a fifth year PhD scholar under Professor Krishna P. Kaliappan in IIT Bombay. This course is taken by Professor Krishna P. Kaliappan, and this is our second tutorial session. So, let me share my screen. Is it visible? Okay, so today we will start with the this problem. The prop question is the major product of the reaction. So here they have given a cyclohexenone derivative and this is proline derivative. So first step is the treatment with this methyl vinyl ketone, and in second step on treatment with the sodium acetate, acetic acid, water and heat condition, what will be the major product out of this four options. So we will wait for a couple of minutes so that you can try this problem, as well as we will see whether anyone else is joining also. So this is an example for a Robinson annulation reaction. So Robinson annulation reaction is basically a Michael addition followed by aldol condensation reaction. So it is known as Robinson annulation because annulation means a formation of a ring. So other than the ring already present in the molecule, we are constructing one more ring to the molecule. That is why it is called an annulation reaction. So it will be following a Michael addition and aldol condensation sequence. So we will see which is the correct answer for this question. So this is the correct answer that sorry for that. So this is the correct answer, option A, and the mechanism for this reaction is like this. So in the presence of this proline, first it will form this iminium ion, and this iminium ion can exist in this enamine form as well. Then when we are treating with this methyl vinyl ketone, it will undergo a Michael addition reaction, that is basically a 1,4 addition reaction to form this intermediate. Then what is happening? Aldol reaction is happening, that is from here proton abstraction takes place and this negative charge will attack over this, and then elimination of water molecule will result in this bicyclic system. So this reaction is known as Robinson annulation reaction. I hope it's clear. If you have any questions or any doubts, please feel free to ask. Okay, then now we will discuss one more reaction, and then we will move to the discussion for the last week's lecture content, and then we will discuss some problems based on last week's lecture. So the major product of the reaction, so here the cyanide compound is treated with LDA and THF at minus 70 degrees Celsius to RT, so which will be the major product. And this is a named reaction also, so try to identify the reaction as well. So here the correct answer for this question is second option, and this is an example for base catalyzed Thorpe reaction. Yeah, so that was the just a warm up session about discussing two problems before starting the lecture contents. So now we will move ahead with the discussion on the lecture contents. So the first lecture of last week was about cubane. So there we saw how to construct a cubane and how this total synthesis of cubane evolved over time. And so as we know, this cubane is a non-natural product having four membered rings. So there are in total six four membered rings fused together. So there are some challenges associated with the synthesis of this molecule. The first one, as we said, there are six four membered rings fused together, and considering the retrosynthetic point of view, for doing strategic bond connections and all, first thing we would look up to is there is any functional group in the molecule so that we can plan for the disconnection approach accordingly. But here in cubane there is no functional group, and the six four membered ring fused together system is a highly strained system, and also it is very low molecular weight, around 104, because its molecular formula is C8H8 only. So considering the retrosynthetic point of view, so for the construction of this four membered ring, one reaction we can consider is photochemical reaction, that is 2 plus 2 cycloaddition reaction can result in the formation of four membered rings, where this homo of alkene and LUMO of alkene overlap in the presence of light to form a 2 pi s 2 pi s addition to get a four membered ring. So this is an example of a Cooksen's dione. So here it involves a sequential thermal and photochemical reaction. So this is our diene, cyclopentadiene, which reacts with this dienophile benzoquinone, where one of this double bond acts as the dienophile, and it will undergo, under thermal condition, it will undergo a 4 plus 2 cycloaddition reaction to form this compound. And this compound, in when we treat it with light under ethyl acetate pyrex condition, this double bond and this double bond can undergo 2 plus 2 cycloaddition reaction to get this compound. So this is known as Cooksen's dione. So this is also very similar to that of a cubane, so that is why this intermediate is considered very important in total synthesis or cubane's total synthesis. So considering the retrosynthetic point, how many four membered rings could be made by a photochemical reaction? So the problems associated with that photochemical reaction is its reversibility, stability of starting material, and the possibilities of intermolecular reaction rather than the desired intramolecular reactions. So the major solution for this is to introduce a functional group. Then the question comes, where to introduce this functional group? So the functional group which we are introducing should be easily removed, and it should be we should be able to introduce that functional group very easily. So either this functional group can be introduced with ring contraction or ring expansion. So ring contraction means we are considering a four membered ring from a three membered ring. This is ring expansion. So three membered ring to four membered ring is ring expansion, and if we are constructing a four membered ring from a five membered ring, this is known as ring contraction, because one carbon number we are reducing in the product, so this is ring contraction. So expansion, ring expansion, what is the problem is that here if we start with, for example, if we start with this one double bondo and we treat with this diazomethane, we can get this system. So we have constructed a four-membered ring, but the problem is that here one of the carbon is sp2. But in cubane, as we know, there are no sp2 carbons, so that is one of the drawback. Then considering the ring contraction reaction, we can consider this Favorsky rearrangement. So Favorsky rearrangement, this is the mechanism. So here I have shown that we are starting with a five-membered ring, five-membered this chlorocyclohexanone, and we are getting this cyclopentene carboxylic acid, where all the carbon centers in the resulting compound are in the ring are sp3. So what is the mechanism? First, base will abstract this acidic proton and that will form a negative charge that will attack on this chloride and it will form a three membered like this kind of an intermediate. Then again base will OH minus will attack at this center and this will shift over here, and when it comes back this ring will open and then this negative charge is neutralized by this H plus in water molecule and we will get this carboxylic acid. So this is known as Favorsky rearrangement. So as we can see from the mechanism, rather than ring expansion, ring contraction is the much better way for getting cyclobutane, where we can get all the carbon in the ring sp3. So how many carboxylic acid should be present in our starting material, or one carboxylic acid or two carboxylic acid? So if we start with this molecule, we will be getting this one. And if we start with this one, we will be getting this one. So one carboxylic acid precursor will have one five membered ring and one remaining all four membered ring. Two carboxylic acid precursor will have two five membered rings and remaining four membered ring. So this will be more preferred rather than this one, because when you convert more five member to four member, job will be more simpler, and it is better to consider four membered rings in the end than in the beginning. And the relationship also, where the carboxylic acid should be. So this method was developed by Eaton and Thomas in 1964. Construction of this cubane by the Favorsky rearrangement. Or rather than Favorsky rearrangement, we can say this is a kind of quasi Favorsky rearrangement. So where the bromine was there in the starting material, in the product we can see the carboxylic acid is coming at that position. Here also same, where the bromine was there at the in the product, the carboxylic acid is coming at that position. So 1,3 will be giving 1,3 bromide will give 1,3 dicarboxylic acid. Then we have also seen this construction of cyclopentadienone, how to construct the cyclopentadienone and resulting cubane using this quasi-Favorsky rearrangement, which was developed by this Eaton and Thomas in 1964. So that was a lecture about cubanes, where we saw its retrosynthetic approach, how ring contraction can be made utilized for the construction of cubanes. Now, moving to the next lecture topic, that was about endiandric acids, where we saw the total synthesis of endiandric acid A, B, C, and D. So, as we can see in the structure, it is having one four-membered ring, that is here, one four-membered ring fused with five-membered ring as well as six membered ring. So that is endiandric acid. And this Cyclohexene in this molecule indicates that a Diels-Alder reaction possibility. So endiandic acid D is having two dienes. Here also one diene is there and here also one diene is there. And these molecules are isolated from the leaves of Australian plant Endiandra introsa by Black's group in 1980. And it is very medicinally active compound because it shows antibiotic activities. So in A, B, and C, there are four carbocyclic rings and total eight stereogenic centers. In endiandric acid D, there are two carbocyclic fused ring and four stereo centers in total. So these molecules are found in nature as racemates. So these are the points which we already told. So the in its biosynthetic approach, there was Black's hypothesis that this kind of a tetraene can undergo 8 pi conrotatory electrocyclization, which is obviously thermal, and give this octatriene molecule, which upon a 6 pi disrotatory electrocyclization can give this one, and then an intramolecular Diels-Alder reaction can give this endiandric acid derivative. So all this endiandric acid derivative can be constructed by this combination of this pericyclic reaction, that is electrocyclic and Diels-Alder reaction. So the first total synthesis for this endiandric acid A, B, C, D was reported in 1982 by Nicholas group, where the key reactions were intramolecular Diels-Alder reaction to set the intermediate, which results in the key intermediate, and using that one particular intermediate, they have achieved the total synthesis of all this endiandric acid A, B, and C and D via a series of electrocyclization and Glaser coupling reactions. And these are some of the new terms which we saw in the lecture, that is Lindlar catalyst, Glaser coupling, electrocyclization, Diels-Alder reaction, and in particularly this synthesis they are utilizing intramolecular Diels-Alder type 1 reaction. So now we will see some of those reactions. So Lindlar catalyst, what is a Lindlar catalyst? So Lindlar catalyst is the combination of this 5% palladium calcium carbonate and this lead diacetate and quinoline. So the mixture of these three, palladium, calcium carbonate, lead acetate and quinoline, is known as Lindlar catalyst. And where it is used? So Lindlar catalyst is particularly used for the reduction of alkynes to cis alkenes. So that is a specialty. It will give only cis alkenes. So an over reduction is also not happening. Alkynes can be converted into corresponding cis alkenes by this Lindlar catalyst under hydrogen atmosphere. Now, the next reaction which we saw in the total synthesis of endiandric acids was Glaser coupling. So, Glaser coupling is basically the coupling of two aryl alkynes by utilizing this copper chloride and this ammonium hydroxide. So, this intermediate is forming, and in the presence of oxygen atmosphere, this intermediate will couple with another intermediate of the same molecule, same type, and it will give this coupling product. So, that is known as Glaser coupling. Now, moving to the next lecture. So the next lecture was about penicillin. So the penicillin was discovered by Alexander Fleming, as we all know, in 1920s, and it is produced by the malt Penicillium notatum. And this structure of penicillin 5 was discovered by XRD by the professor Dorothy Crawford Hodgkin. So as we can see from the structure, it is having this four-membered beta-lactam ring, which is fused with another five-membered ring, and this is the core structure of all the penicillins. And there is also an acetylated amino group that is present adjacent to this carbonyl group. So basically, this type of four-membered lactams are unstable and quite reactive. It does not exhibit stability of a typical amide due to the fused five-membered ring. So now we have to see how to construct this beta-lactam rings. So these beta-lactams are basically acetidinones, which are antibacterial agents. And this carbonyl derivatives of acetidines contains CO group at this second position. So one of the peculiarity of this beta lactam is normal amide shows its IR stretching frequency at 1660 centimeter inverse, but in IR this beta acetidinone shows its stretching frequency at around 1735, 1735 and 1765 centimeter inverse. Now, the synthesis of this beta lactam could be done using many reactions like cyclization reaction, cycloaddition reaction, ring expansion reaction, insertion reactions, and also from acetidines. Considering this cyclization reaction, beta amino acids in the presence of certain reagents including acyl chlorides, phosphorus trichlorides, thionyl chlorides will give the beta lactams. So beta aminopropionic acid are not cyclized to beta lactams on heating but undergo elimination reaction providing amines and acids. So that is one of the method for the construction of this beta lactams. Then we can get this beta lactams by the cycloaddition reaction also. For the cycloaddition reaction, our substrates will be an alkene, and if we consider an isocyanate, isocyanate means SO2Cl, this N plus double bond C, no, here plus is not there, N plus. Yeah, so this is an example for an isocyanate. So this upon this 2 plus 2 cycloaddition with this alkene can also give this beta lactams. Then ring expansion reaction. That is a three-membered ring like this. Here OH and another substituent is some N with some halide and some R group. So this can also give in presence of the silver salt and all, this group will be leaving and the expansion will be taking place to get the beta acidity, this beta lactam rings. Then another reaction is insertion reaction, which is basically carbene insertion reaction. Then as we already told, from acetidines also we can construct this beta lactam rings. So these are the examples for the reactions where we can construct this beta lactam ring: cyclization reaction, cycloaddition, ring expansion, insertion reactions, and from acetidines. Now, moving to the total synthesis of penicillin, the Professor J. Sheehan from MIT has reported the first total synthesis of penicillin in 1957, where they used starting materials like valine and tertiary butyl thalidommalonaldehyde for D-penicillamine hydrochloride. So this was their retrosynthetic strategy, where they have planned for brucine for the resolution of a racemic mixture, and this tertiary butyl thalidommalonaldehyde and D-penicillamine hydrochloride will give D alpha as well as D gamma isomers. So here this phthalimide derivative, they are cleaving with a hydrazine, and utilization of a DCC coupling at the final stage will give this penicillin 5 as its potassium salt. So the key steps of this reaction involves Michael addition, mild lactonization using DCC, and one of the side reaction is as a lactonization. Now we will see what is DCC coupling. So DCC coupling is basically the coupling between these amines and acid, where we are using this DCC as a this coupling reagent. So first what we'll do, so this is the structure of DCC. So that DCC nitrogen will take a proton from this carboxylic acid. It will form this intermediate, and so this bond will attack here, and this oxygen will attack over this carbon to form this intermediate. Then again what is happening is that this amine will attack on this carbonyl carbon, and this bond will shift to here to form this intermediate. Then elimination will take place, so this will come here, and this is a good leaving group, and this dicyclohexyl urea will be the byproduct, and we will get this couple product, acid amine couple product. So an amide will be formed from acid and amine by using this DCC coupling. So the full form of DCC is dicyclohexyl carbodiimide, and the byproduct which we are getting is dicyclohexyl urea. Then the next lecture was about thyramycin. This is also having four-membered ring, and the similarities with penicillin and thyramycin are both are having a four-membered lactam, but here in five-membered ring, the sulfur is part of the ring, where in penicillin it was not a part. And this also exhibit antibacterial properties, and it is a constituent of fermentation broth of soil microorganisms Streptomyces cattleya. So in selective synthesis of this Thyramycin was reported by Merck from commercially available L-aspartic acid. So there we have seen how a transient protecting group can be used like TMSCl. So transient protecting groups, it is means it is protected and deprotected in one or two steps, and we are not keeping it for longer time. Then we have seen how they have utilized Finkelstein reaction, this mercury chloride, mercury for removing mercuric oxide for removing thioketal, then diazo introduction by tosyl acide, para-nitrobenzyl deprotection by hydrogen palladium carbon. And it is a racemic method which is operationally simple. And we have also seen a racemic method which is operationally simple, where they are utilizing an enamine and a ketene, and then Meldrum's acid as well as intramolecular Mitsunobu reaction. And here, intramolecular carbene insertion is the key reaction to construct this strained bicyclic nucleus. In both this enantioselective synthesis as well as in racemic method, this intramolecular carbene insertion is used to construct this strained bicyclic nucleus. Now we will see what is a Mitsunobu reaction. So Mitsunobu reaction is a type of SN2 reaction which we do on alcohol or alcohols. Basically, it is an SN2 reaction and it will be inverting the stereochemistry of that sender as well. So here we are using this diethyl azo-dicarboxylate and this PPH3. So this PPH3 lone pairs will attack over this nitrogen and it will form this intermediate. Then again, this nitrogen will take this proton from our nucleophile, making our nucleophile available. And then the oxygen of our alcohol can have an affinity towards this phosphorus of this PPH3. It will coordinate with that, resulting in this intermediate. And this will leave as the byproduct this diethyl 1,2 hydrazine dicarboxylate. And this then upon this elimination of this pph3 oxide, where our nucleophile will attack at this carbon to get this substituted product, and the byproducts of this reaction is triphenyl phosphine oxide. So we are using an alcohol, a nucleophile, diethyl azo-dicarboxylate and triphenyl phosphine, and the byproducts are diethyl 1,2 hydrazine dicarboxylate and this triphenyl phosphine oxide. So now the last lecture of last week was about prostaglandins. So it is also having this five-membered ring, a cyclopentane with this two side chains. That is the core, which is known as this prostanoic acid, and there are these are discovered in 1930 by von Euler, and the structure was correctly elucidated in 1966. So they are carbocyclic oxygenated C20 molecule, and the classification of this prostaglandin is based on the nature of functionalities present and the number of unsaturation in the two side chain appendages. So this PG stands for prostaglandin, and this A, B, C means the all are having double bonds but in the different position. So that is why this A, B, and C. In next, PGD and PGE means they are having no double bond, but there is a hydroxyl ketone and beta hydroxy group is there. In PGF, two hydroxy groups are there in the cyclopentane. There are two PGFs as but it is not shown here, PGF alpha and PGF beta. PGF alpha means both the hydroxyl groups are alpha position. PGF beta means one hydroxyl group is in the beta position. And this subscripts are also used in some of the prostaglandins, which indicates the number of double bonds in the side chain. For example, PG1 alpha, PG1 2 alpha, like that. So the major synthetic challenge of this prostaglandin is its Hef series having 5 chiral centers and 4 are contiguous, and hydroxyl is away from the cyclopentane at C15 position. So that is one of the problem. and one side chain has cis and other side chain has trans double bond in the prostaglandins. The presence of beta hydroxyketone makes it unstable in the case of D and E. So this Corey group reported this total synthesis by bicycloheptane approach, where the cleavage of a substituted bicycloheptane provided trisubstituted cyclopentane with correct stereochemistry. And the key reactions involved in this total synthesis are Diels-Alder reaction, Baeyer-Villiger oxidation, and iodolactonization for the construction of the five-membered lactone ring. So this lactone is known as Corey's lactone, and this is used in the total synthesis of PGE2 alpha and PGF2 alpha. So this is Bayer Villiger oxidation. So basically we will be using metachloroperbenzoic acid or any peroxy acid and a carbonyl compound, and an oxygen is getting inserted between an alkyl group and this carbon. So what is happening, this lone pair of oxygen will attack at this carbonyl carbon center, and this intermediate will form, and when this will come back, this R group will migrate to this oxygen and this will be eliminating as this acid. So this will be our major product. And the migratory aptitude is in this order: proton is having more migratory aptitude than tertiary alkyl, then cyclohexyl, then secondary alkyl and aryl, then primary alkyl, and methyl is having least migratory aptitude in the case of Baeyer-Villiger oxidation. So now we will start the problem discussion. So first question is this one. So treating this compound with this H2SO5 and Na2HPO4, which will be the major product out of this four option. So I will give you a couple of minutes to answer this question, then we will discuss the answer. So here the correct answer for this question is option C, that is this one. And this is an example for Bayer vinegar oxidation. So you can have a question why the oxygen is coming here rather than this position. That is because as we saw the migratory aptitude, the secondary ring carbon is migrated preferentially over the primary ring carbon with retention of configuration in the migrating group. So which clearly show that the concerted nature of this rearrangement steps. Now, some more example we will see about this Bayer vinegar oxidation, and we will move ahead with the discussion on other topics. So, what is the major product in this reaction? MCPBA, DCM condition, which we will be getting as the major product. So here the correct answer of the question is option A. And as we said, the same reason applicable here also, that is due to the migratory preference, it is coming at this position. Now, next question. This compound on treating with this K2SO5 on hydrated SiO2 condition, which will be the major product out of the four options given here. So here the correct answer is tertiary butyl benzoate. Tertiary butyl benzoate means, I will draw the structure here. So this is a benzene ring. Then here C double bond O. Then one more oxygen. So that oxygen is coming from that K2SO5 and then this tertiary butyl group. Then the next question is Bayer vinegar monooxygenase upon treatment with this compound, which will be the major product. So here also, as we can see, the correct answer will be option A because of the migratory aptitude. Now another reaction, MCPBA in presence of sodium carbonate upon treatment with this compound, which will be the major product. So here, as we can see, this is forming in 65 percentage and this is forming in 35 percentage. So what is the reason? This is camphor. So bare villager oxidation of camphor with MCPBA in buffer condition gives the major product that is formed due to the migration of tertiary bridgehead carbon rather than the methylene group. So this is migrating rather than this group. The Krieg intermediate that can be formed here can either be exo or it can be endo attack of peroxy acid. If it attacks in exo fashion, the migration of bridgehead is more favored, as we can see in this intermediate, since it goes through a chair type of transition state. So here migration of methylene carbon is not that much favored because of this boat shaped transition state. So the correct answer will be this one, that is option A. So that was the discussion about this bare vinegar oxidation. Now try to answer this question. This compound upon treatment with the sodium methoxide and diethyl ether, which will be the major product out of these four options. So this is an example for this Favorsky rearrangement which we saw already. So when we are using this sodium methoxide, it can abstract proton from here forming this carbanion which will attack over this center and forming a three-membered ring. So this will be the intermediate. Then in the next step, this OMe will be attacking at this carbonyl carbon center. So this will come as O minus, and when this O minus will come back, this ring will goes here and this negative charge will come over here and this bromide will leave to form this final product, this alpha beta unsaturated compound. So the correct answer will be option 3. So this is an example for Favorsky rearrangement. Moving ahead with the next question. This compound upon treatment with this iodine and potassium iodide in presence of sodium carbonate, which will be the major product. So here what is happening is that this iodine or Ki can form this iodonium ion over this center, so that will be resulting in this species. So here this iodonium ion will be there, and here this carboxylic acid will be there. So in the next step, what will happen? This O minus can attack over this carbon center and can open this iodonium ion, and it will result in the formation of a 5-membered ring. One, two, three, four, five. Now the question is that, so either it can be this product A or B. Now the question is that either it will attack from the same face of the iodonium ion or opposite face. So if it attack from the opposite face, it will be A. If it attacks from the same phase, it will be B. So here the attack will be in ascending fashion. This O minus will attack from the opposite phase of this iodonium ion, and it will be giving this product A as the major product. So the correct answer is option A. Now the next question is this one. So here, this what is this reaction? Like this compound is converted into this compound. So what is happening here actually? So here this is an example for 1,5 hydrogen shift. So what is happening is that this hydrogen this hydrogen at this position is getting shifted, migrated, like this bond will shift to here, and this double bond will shift over this position, and this will take this hydrogen, and this is an example for this 1,5 hydrogen shift reaction. So the correct answer will be 1,5 hydrogen shift. So here is one mistake, it is not methyl shift, it is 1,5 hydrogen shift. Then the next question. So this conversion, that is, this is an electro ring opening kind of reaction. So this octatetraene, upon heating, we will be getting this compound, and this is 6 pi or 4 pi cyclization that we have to identify first, and then we have to identify whether this is disrotatory or conrotatory conversion. So as we know, 6 pi under thermal condition would be giving disrotatory electrocyclization, and as well as it will undergo under photochemical condition, it will be undergoing conrotatory conversion. Whereas in the case of 4 pi system, under thermal condition, it will be undergoing conrotatory electrocyclization, and under photochemical condition, it will be undergoing disrotatory electrocyclization. So this is an example for 6 pi disrotatory electrocyclization. Now what we will see, what is this disrotatory and conrotatory electrocyclization. So if we consider a double bond like this, so here as we can see the substituents, here this hydrogen and here is one hydrogen. So here this both this hydrogen are in trans stereo configuration, and here both this hydrogen are in cis configuration. So what will happen is, as this carbon rotates with the lobes, the substituents also will rotate. So counterclockwise rotation is known as conrotatory rotation. So this will rotate here and this will rotate here, and we will get this intermediate, and this we will be getting. So like conrotatory means same side rotation, disrotatory means opposite side rotation. So in the case of conrotatory clockwise rotation, we will be getting this intermediate and we will be getting this one, which both are same only. And in the case of disrotatory, as we can see here, one will rotate in clockwise and one will rotate in anti-clockwise direction, and we will be getting this intermediate, which will result in this trans product. So that is the difference between conrotatory and disrotatory electrocyclization. So 6 pi under thermal condition will undergo disrotatory. So here only this is this, and so here we can say it is a 6 pi electrocyclization reaction where one of the double bond is not participating in the reaction, and 6 pi under thermal condition will be undergoing disrotatory, and we will be hitting this cis configuration. And if it was photochemical, it will undergo conrotation, and in 4 pi system under thermal condition it would be undergoing conrotation, and in photochemical condition it would be undergoing disrotation. Now we will move ahead with the discussion on week 1 assignments. So the first question is, what is the difference between semi-synthesis and partial synthesis? So the four options given are, first option is semi-synthesis, the synthesis of a portion of natural product, whereas partial synthesis, the synthesis of a given molecule from an advanced precursor related to it. Second option is semi-synthesis, the synthesis of a given molecule from an advanced precursor related to it, whereas partial synthesis, the synthesis of a portion of a natural product. Third option is semi-synthesis, the synthesis of a portion of a natural product, whereas partial synthesis, the synthesis of a key intermediate that has been already converted into a target molecule. Now, last option is semi-synthesis, the synthesis of a key intermediate that has been already converted into the target molecule, whereas partial synthesis is the synthesis of a given molecule from an advanced precursor related to it. So, out of these four options, which is the correct answer? So, this we have seen in the introductory lectures, that is week 1 lectures. So here, as we know, the correct answer is option B. So semi-synthesis means an advanced precursor which is already available in the nature. We are starting the total synthesis from that advanced precursor and we are synthesizing that natural product. And partial synthesis means we are synthesizing only a portion of the natural product, like a particular fragment or a particular side chain or a particular ring system. We are synthesizing that only. So that is known as partial synthesis. Now, moving to the second question, name the first organic molecule synthesized in a laboratory. So, the options given are acetic acid, glucose, urea, and tropinol. So, which among this is the first organic molecule to be synthesized in the laboratory? So, the first organic molecule to be synthesized in the laboratory is urea. And who coined the term synthesis first? So the term synthesis was coined by Kolb, and he used this term synthesis first in the history. And which of the following method cannot be used for the preparation of three-membered rings? So here we, as we know, the Simon-Smith reaction, sulfur halides and SN2 displacement of 1,3-diketone or beta-keto ester could be employed for the preparation of three-membered ring, while the cycloaddition of imines with ketene is not a non-reaction for the preparation of construction of three-membered rings. Now the next question is the synthesis approach where two or more fragments are synthesized separately and coupled at a later stage to obtain the target molecule is known as. So this is an example for convergent synthesis where we will be synthesizing two or more fragments and that are coupled to obtain the target molecule. So that is known as convergent synthesis. Now the next question, identify the major product in the following transformation. So this compound upon treatment with this potassium hydroxide and this dibromo compound in presence of this tetrabutyl ammonium hydroxide, which will be the major product. Tertiary butyl ammonium hydroxide, which will be the major product. So here what is happening is that this base will abstract this proton from this center and that can attack over this carbon. Then again a base can abstract this carbon and again a base can abstract this. So here the correct answer is this option C. So what is happening? So this base can abstract this proton and it will attack over this center and then again that base can remove one of this bromide and it can attack on this carbon and again this bromide will be removing. So that's how it will give this option C as this major product. And then in the presence of this potassium hydroxide, this ester hydrolysis is also taking place to convert this carboxylic ester into this carboxylic acid. Moving on to the next question, identify the correct intermediate A in the following reaction. So here this diazo compound is treated with this rhodium acetate. So here they will give this A, which upon this phthalimide derivative, we will be getting this as a result of 1,3 dipolar cycloaddition, that is 3 plus 2 cycloaddition reaction. So uh, which will be the intermediate out of this four options. So here the correct answer is this option A. So here it is forming a carbenoid type of rhodium carbenoid type of intermediate, and that will attack over this carbonyl oxygen to form this particular intermediate. So this is the dipolarophile dipole, and this is the dipolarophile which will undergo 3 plus 2 cycloaddition reaction to give this product. Moving to the next question, the major product A formed in the following reaction. So this compound upon treatment with this diethyl zinc and this diiodomethane in presence of in DCM solvent at 0 degrees Celsius, which will be the major product. And this is a named reaction. We have seen last week also examples for this reaction. So here, this is an example of Simmons-Smith reaction, that is cyclopropanation reaction, and the correct answer would be option D. And the reason is that, so cyclopropanation here, it is this, either it can be alpha or it can be beta. So because of this hydroxy group, it is actually directing the cyclopropane ring, and it will be in the same phase of that is or that of this hydroxyl group, because that oxygen will coordinate with the zinc, and that is only directing this. So the correct answer will be option D. Already we have seen the detailed mechanism and explanation for this in the last week's tutorial session. Now moving to the next question. Identify the major product formed in the following reaction sequence. So this particular nitron, upon treatment with this alkene and then LAH reduction, which will be the major product? So this is an example for 1,3 dipolar cycloaddition reaction followed by reduction reaction. So the correct answer would be this question. So first that 1,3 dipolar intermediate will form, then that amide reduction will be done by this LAH to give this option B. Now, the last question of this week, one assignment, the correct structure of the major product formed in the following reaction sequence. So, this particular compound, upon treatment with this dirodium acetate, tetraacetate, and this alkyne, which will be the major product out of this four options. So, here already we have seen the intermediate formed in this reaction. So, like this particular intermediate, it will be forming, and then a 1,3 dipolar cycloaddition will be taking place. There it was phthalimide, and here it is the alkyne to form this one. So the correct answer here is option D. So this is also an example for 3 plus 2 cycloaddition reaction through this carbene intermediate, rhodium carbenoid. So that's about the discussion on week uh, two tutorial week 2 lecture contents, and we have seen beginning we have started with the discussion of some problems regarding aldol, Michael addition, Robinson annihilation, and Thorpe reaction. Then we had a detailed discussion about the week 2 lecture contents, where we have gone through all the lectures and just revised what are the key reactions discussed in each of the total synthesis. And then we have also seen some examples for this Bayer Villiger oxidation, and then we have solved some more examples for this Favorsky rearrangement and some related reactions. Then we have solved this week 1 assignment as well. So I hope this session was interesting and you had a great time listening this. So if you have any questions, you can come up anytime, or you can ask in the next tutorial session, which will be on the coming Saturday at the same time. So thank you for joining. Thank you.